All right, now we're going to go into a little bit more detail on the Lorentz transformation, and I'm going to do an example on how to use that velocity addition formula. So you've seen this already in this chapter, and this is just review from Physics 105. So again, special relativity deals with inertial reference frames, no accelerating reference frames. So all we know is that S prime is moving relative to S. We know nothing about S. We don't care. And S prime is moving with speed v, or velocity v, relative to S. All right? And, okay. Uppercase, right? So the velocity of this particle is measured to be v in frame S, little v that is, in v prime, little v prime, in frame S prime. That should be nothing new. Okay, so these were the Galilean transformations. And they're fine as long as the velocity of the particle is much, much, much less than the speed of light. And you can see that, there's no time dilation. Okay. So that's Galilean or Newtonian. And then this is what Einstein figured out. But again, Lorentz had already done it, but he didn't know what to do with it. So whatever's in yellow is the change or the difference from the Galilean. So you can see that the times are not the same. You can see there's this gamma because the distances, the length contraction and all that. Okay, so there you go. All right, let's see. Okay, so these are the distance and the time, but we want to get the velocity. So here's the velocity. So this is the Galilean, right? If you're in a car moving at 60 miles an hour and you stand up and ignore air resistance, you throw a ball at 100 miles an hour, somebody on the road would measure the ball going 160 miles an hour, right? Just add them. But with relativity, it can't be right because remember, everybody measures the speed of light to be the speed of light. And so if I were in a car going 100 miles an hour and I flashed on my headlights, this would be wrong because according to this, the speed would be greater than the speed of light. It would be the speed of light plus 100 miles an hour, and we know that's wrong experimentally. So this is what Einstein came up with using the Lorentz transformation. And so this is going to make it smaller, right, because it's in the denominator, and it's positive, right? It's positive. Okay, now the way that this equation works is you will never exceed the speed of light. So let's try it. So let's have a rocket, and let's say that the rocket is moving at, velocity 0.99 c, and then the guy in the rocket turns on the light, right, the headlights or something like that, which goes at the speed of light, right? Okay, so u equals u prime 0.99 c plus c all over 1 plus 0.99 c times c over c squared, right? Just using a formula. So these c's kill that. And then on the bottom we have 1 plus 0.99, which is 1.99, 1.99. And here, factor out the c, and we get 0.99 plus 1, right, which is 1.99, 1.99, which cancels the numerator and denominator, so we just get c. All right? I mean, you should play with it yourself. But put any numbers in here you want, and you'll see that this will never, never, never exceed c. It will never exceed the speed of light. Because nothing can travel faster than the speed of light. All right. Okay, now, in my opinion, the easiest way to do this is just to use that formula that we learned in Physics 105. So here. So we want to, all right, so there's Abe and there's B, right? A, B, whatever, okay? And then there's a probe, okay? So we want to find the velocity of the probe relative to Abe. So how did we do that in Physics 105? Well, Remember that silly little formula that works, right? So let me do it over here. So we want the velocity of the probe relative to A. So the funny formula, you remember hopefully, the P goes there, the P goes there, the A goes there, the A goes there, and what's the other reference frame? B, right? Remember that from 105? So left, left, right, right, and these guys cancel, all right? I mean, it works. So let's just do it. Okay, so let's just do it. All right, so this is the classical formula that we learned in 105, but now we have the relativistic formula. So, you know, the part in yellow is the same, right? But now we have that new denominator. So 1 plus that times that over c squared. Isn't that great? You know, it's just this, right? The bottom is this times that over c squared plus 1. So just the classical formula with this new denominator. Okay, so let's do it. We're going to do it. Oh, okay. I guess we don't have any numbers, so that's the answer, right? Okay. Now let's do a real problem. So make sure you remember this, or make sure you understand this from 105. Okay, let's do it. So rocket ship A is moving away from Earth at 0.6 c in a positive x direction. Rocket ship B is also moving away from Earth in the same direction. It's moving at 0.5 c, as measured by rocket A, though, right? So how fast is rocket B moving in Earth's reference frame? Oh, gosh, right? Okay, so wow, all right. So let's just use the formula, right? So what do we want? How fast is rocket ship B moving relative to Earth? So we want V, velocity of B relative to Earth. So just use your formula, right? So VBA plus VAE, right? B's on the left, B's on the left. E's on the right, E's on the right, the other guys cancel. And then you just use this new part from relativity. So now let's do it. Okay, so what is VBA? So that's velocity of B relative to A. So let's see, where's that? Rocket B is moving at a velocity of 0.5 c as measured by A. So the velocity of B relative to A is 0.5 c. Okay, now we also want to get this. So we want VAE. Rocket A is moving away from Earth at 0.6 c. Great, 0.6 c. And then we just plug and chug, right? So therefore, VBE equals VBA 0.5 c plus VAE 0.6 c all over 1 plus the product. And if you plug in all that, well, let's just do it. You get 1.1 c. And on the bottom, this works out to be, well, 0.5. A half of 0.6 is 0.3, right? So it's 1 plus 0.3. And if you work that out, I promise you get 0.85 c. Now, big caution here. You have to incorporate the directions, right? If it's, positive x, we get a plus. But what if something was moving, like what if one rocket was going this way and the other rocket was going that way? Then you have to have a minus sign, right? Just like, 105, okay? So just be careful. If something moving to the left, we say it's positive. If something's moving to the right, we say that the velocity is negative. So don't forget little trivialities like that or you're going to be in big trouble. Okay, so there you go. And this, again, what would Isaac Newton say? Isaac Newton would just say 0.6 c plus 0.5 c equals 1.1 c. Well, that's greater than the speed of light, so you know it's wrong. So you do it correctly, and you see the answer is 0.85 c. So there's a big difference, right? Okay, so we've talked about relativity of space, time, simultaneity. We talked about how to add velocities correctly. What else is different? Momentum. Momentum is different. Why is momentum different? Well, think about it. Classically, okay, here. Classically, there's no limit to the speed, right? So we're going to use Randy Knight notation, okay? So classically, momentum is mass times velocity. I'm using the u because the v is the reference frame, right? Now, classically, there's no limit to the u, right? So the momentum can be as large as you want. But relativity says, wait a second, the speed has to be less than or equal to the speed of light. So that means we have to fix this, right? Because it's wrong. It's wrong when the speed approaches the speed of light. So we have to fix it in some way. All right, now, so one more thing. Classically, no limit to the speed, right? But also classically, P is proportional to u, right? The mass is constant, P is proportional to u. So if we make a plot, I think I have a plot. Yeah, if we make a plot of P versus u, classically, it's just a line, right? Just a straight line. However, when you do the actual experiment, guess what? It goes like this. Because again, relativistically, you cannot exceed the speed of light. So the relativistic momentum approaches infinity as u approaches the speed of light. Okay, so it just means that we have to fix our formula. And you shouldn't be surprised, right? So guess what? There's the formula. And, we've been having gammas everywhere, so kind of stands to reason we're going to have a gamma again, right? But this gamma is different than the gamma we've had in the past. In the past, the gamma has been the speed of the reference frame. Related to the speed of the reference frame. Here, we put a p there. So it's the gamma of the particle that you're concerned with. So be careful, all right? Got to be careful. Okay, so, it's the same formula, right? 1 minus beta squared minus 1/2 and all that. But, again, u is the velocity of a particle moving in the reference frame. So this gamma p has the speed of the particle moving in the reference frame. So just be careful, that's all. Here's a great example of how important this is. So this is Fermilab. And Fermilab, again, it accelerates protons. Now protons, want to go straight, right? And they're not going to go in a circle unless there's a force making them go in a circle. So they use magnets to make the protons go in a circle. Now, as the protons go faster and faster and faster, what do you want to say? It's harder and harder for us to make them go in a circle, right? Because they have the greater and greater momentum, so you have to turn the magnets higher and higher and higher. Now, this is what would happen according to Newton, right? But according to relativity, as I just said, the momentum goes screeching up there. And so when the particles are going nearly the speed of light, the operators of Fermilab, they have to really crank up those magnets. If they just turn them up according to relativity, the particles would smash into the beam pipe and you'd be done. So they have to really crank up the magnets to compensate for that increased relativistic momentum. Okay? So that's another evidence that relativity is correct. All right, here's a problem for you. A 10 to the minus 6 kilogram particle moves at 0.25 c, so that's relativistic. What percentage error will the classical expression for momentum give? In other words, what you're really figuring out, what's gamma, right? Because, without the gamma, it's just a classical expression. So gamma tells you the difference between classical and relativistic. So in other words, just figure out gamma p. So pause your video and figure out gamma p, please. Okay, so hopefully you've done it. The only difference is you care about the speed of the particle. So gamma p is 1 minus beta p squared minus 1/2 power. So 1 minus, what? Okay, now what's gamma? What's beta p? It's the speed of the particle, 0.25 c. So that means beta is 0.25. So 1 minus 0.25 squared minus 1/2 power, and I promise you, you do that, you get 1.03. Okay? So it's 3% difference, right? 3% difference. Okay. All right. So what haven't we talked about yet? One of the most important concepts of all of physics, and all of chemistry, all of science, energy. So we got to talk about energy. I mean, when you think of Einstein's theory of relativity, what comes in your head? E equals mc squared. We haven't even talked about it yet. So we better talk about it. All right. So we're going to talk about conservation of total energy. Conservation of total energy. Okay. Now we're talking about relativistic particles. Relativistic particles have a huge amount of kinetic energy, right? And so basically the kinetic energy is much, much larger than the gravitational potential. I shouldn't write like that. Kinetic energy is much greater than the gravitational potential energy. So if that's the case, we're just going to ignore it, right? Just ignore the gravitational potential energy. It's total, okay? And that's a good approximation. All right, so therefore, you know, the total energy is just K plus UG, but we're ignoring the UG, so all we have is really the K, right? The kinetic energy. All right? Now, again, we know that we're going to have to fix this equation because, you know, kinetic energy classically is 1/2 mv squared, and so classically V can be anything, and so K can go to infinity, and we know that's ridiculous because the velocity has to be less than or equal to c, so we know we have to fix that equation. So let's do it. Okay, now I'm not going to derive every little thing here, sorry, but I'm going to do a lot. Okay. All right, so Einstein, he did a lot of calculating, and he figured out that the total energy of a particle of mass m and moving at a speed u is equal to gamma mc squared. Okay. So that's what he showed, but we want to I want to show you why, all right? I want to show you why that's true. And because when we show you why, we're going to talk about E equals mc squared, which is totally cool, right? All right, so there you go. So we're going to consider a case where U is much, much less than C, right? So we're going to say that something's going kind of slowly, you know, relative to the speed of light. All right, let's look at gamma mc squared. So gamma p mc squared. Well, what's gamma? Well, you know what gamma is. It's 1 minus beta squared to negative 1/2. All right, but what's beta? It's the speed over the speed of light. So gamma is 1 minus u over c squared, whole thing negative 1/2, times mc squared. Agree? All right, that's totally cool. Now, remember that math trick? Remember the math trick I showed you a little while ago? Oh, let me write nicely. 1 minus x to the minus 1/2 power equals 1 plus x over 2. And that was only true if this x is much, much less than 1. Well, what I said is that the speed is much, much less than the speed of light. So that means this thing is much, much less than 1. So we can use that approximation. Great. So now we're going to have 1 plus u squared over 2c squared, right? Because our x is u squared over c squared. So we have 1 plus u squared over 2c squared times mc squared. Let's multiply it out. mc squared plus mu squared over 2, right? This c squared kills that c squared. All right, so mc squared plus mu squared over 2. Okay? Now, what's this? Let me write this differently. Let me say 1/2 mu squared, okay? What's that? That's just the kinetic energy, our good old friend from Physics 105, the kinetic energy. Okay, now look, this is energy, right? Well, if this is energy, what does this have to be? It has to be energy. It has to be energy, right? Okay, but wait a second. I don't see any velocity. I mean, it has the speed of light, but I don't see any velocity of the particle here, but I see m. So this energy is related to the object's mass, right? So they're going to call this rest energy. Rest energy, right? Rest energy, E0. Okay. All right. So look, Einstein was right, right? This is the total energy. The total energy equals the kinetic energy plus something new. This new thing is the rest energy. So that means, according to relativity, even if something is not moving, it has energy just due to its mass. So here's the new equation. Oh, all right. So the total energy, remember, we're ignoring gravity because there's nothing compared to, K or E0. So the total energy of a particle is the rest energy plus the kinetic energy. And both of those equals gamma mc squared. Okay, now there's more to it. Let's keep going. Let's get a new equation for kinetic energy, because we know we have to get a new equation for kinetic energy because the classical one is wrong. Well, it's not a big deal. So we have E total equals E0 plus K, which equals gamma mc squared, right? All right, so therefore K is just E total minus E0, right? And what's E total? Gamma mc squared. What's E0? Just mc squared. Factor out the mc squared gamma minus 1. So that's a kind of a weird equation, right? Sorry, that's what it is. So this is the relativistic equation for kinetic energy. And as usual, it has a gamma in it, right? I mean, surprise, surprise. Okay. Let's see. Let's write this equation here in a more useful way. All right. This is constant, right? Because, total energy is conserved. So this is constant. So let's write this in a more useful way that we can use again and again and again. And this is what we did when we studied that, when we did energy, So we have E0 plus K is constant, right? It's constant. So we can say E0 plus K initial equals E0 plus K final, because it's always constant, all right? Oh, whoopee. Well, just hold on. You'll see that's useful. Okay, what's E0? It's mc squared, right? So we have mc squared initial plus K initial equals mc squared final plus K final. Now, c squared, I mean, come on, it's a number, right? So maybe it's silly to write it like that. Let's write it like I have over there. Just put the initial here. Same over here. Put a final there. Okay? Now, what does that imply? It implies that the mass can be transformed into kinetic energy, right? It means that the mass is not conserved, because we have initial mass and we have final mass. Okay, so mass can be converted into kinetic energy and vice versa. So when you learned in high school chemistry that mass was conserved, it's a total lie, all right? But I mean, it's okay. It's totally fine as long as you're not dealing with like relativity and things like that, all right? But anyway, so mass is not conserved. And I'm going to show you some examples of that right now. All right. Oh, yeah, here's the man. I'd like to have that stamp, huh? Boy, oh boy, oh boy, that'd be awesome. Okay, so let's learn a little fun stuff. So here's a virus. Funny talking about virus now, right? Okay, there's a virus, 10 to the minus 7 meters. And then what a virus is made out of? Molecules, 10 to the minus 9 meters. Molecules are made out of atoms. Here's an atom, 10 to the minus 10 meters. What's in the center of an atom? A nucleus, 10 to the minus 14 meters. What's a nucleus made out of? Protons and neutrons. So here's a proton, 10 to the minus 15 meters. What's a proton made out of? A quark. Well, quarks, plural. Quarks. Quarks are less than 10 to the minus 18 meters. We don't know if there's anything smaller than a quark. We're looking, but we don't know yet. Okay, so when I was in high school, we didn't know about quarks. That came later on, all right? So we were just taught the smallest things in nature are electrons, protons, and neutrons. But again, protons and neutrons are made of smaller things called quarks. And there are 6 kinds of quarks. Well, it depends how you count. So the first ones that were discovered were the up and the down. They come in 3 varieties. But we'll just say 2, okay? Up and the down. Then the next couple that were discovered were the charm and the strange. And then the third group that was discovered was the top and the bottom. So here's my opportunity to tell my physics joke. So my PhD was done at Fermilab, and we were learning about charmed particles, right? So I had a very charming experiment. Thank you very much. Okay, now let's talk about this top quark. It took a long time before they discovered the top quark because it was so, well, I'll tell you in a minute. Okay, so the top quark was discovered in 1995 at Fermilab, and this is how they did it. The top quark has a lot of mass, so they had to make the protons and the antiprotons that were colliding be incredibly fast. Because remember, mass can be converted into energy. All right, so here's how they did it at Fermilab. I mean, for quite a while at Fermilab, they just knew how to accelerate protons. But then later on, they figured out how to make antiprotons. And so they had the protons going one way and the antiprotons going the opposite way so they could have head-on collisions. So this is what they did. So here's the proton beam. Here's the antiproton beam. So they collide, right? They collide. And they annihilate each other. So for a very brief fraction of a second, there's pure energy. And then that energy is converted into mass. Now here's what's amazing. Look at this picture. Why would they draw the top and the antitop so large, you know, compared to the proton and the antiproton? Here's why. So here's the reaction. The proton smashes into the antiproton, and they annihilate each other. It's pure energy, and then out of the energy, you get a top and an antitop. And these guys don't live very long, the top and antitop, so they shortly decay into other things which we don't care about. But here's the important thing. The mass of the top is 182 times the mass of a proton. Now, when you think about that, that's insane, right? That's like shooting a marble at another marble and getting, I don't know, a bowling, 2 bowling balls out. That sounds insane, don't you think? But that's truth. I mean, that's what happened. So how do you explain that? Where did all this mass come from? I mean, here's these little tiny protons and antiprotons forming these gigantic top and antitop. Where did the mass come from? Right there, right? So what we're saying, I mean, why did it take until 1995? Because they had to make the accelerator make these protons and antiprotons go really, 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 really fast. So what happened is that mi, that's the mass of the proton and the antiproton, and there's the kinetic energy of the proton and antiproton. So some of this kinetic energy became the mass of the top and the antitop. So energy became mass. So that's kind of cool, right? That's what Einstein predicted. Okay, here's another example. So this is it's a particle called a Z0. It was discovered in Geneva, Switzerland, at that big accelerator over there in 1983. So they discovered it there, but most of the work to understand it was done at Stanford in the United States. So this is the Stanford Linear Accelerator, SLAC, Stanford Linear Accelerator Complex. So it's a collide. Okay, so when it was first built, this is 2 miles long. So you just accelerated electrons and they smashed into a stationary target. That's how it was used for many, many years. Then they made it a collider. So you accelerate the electrons in one beam. Well, you accelerate electrons and anti-electrons. And so you have the electrons go this way, the anti-electrons go this way, and they smash, they collide right there in this gigantic detector, you know. All right, so that's how they make the Z. So the electron, that's an E minus, collides with it's called a positron, positive electron, right? So electron collides with an anti-electron or a positron, and they make this neutral particle called a Z0. Now here's what's incredible. The mass of the Z is more than 89,000 times the mass of, you know, 2 electrons. The electron has the same mass as the anti-electron, all right? So the Z is 89,000 times the mass of what the particles that formed it. I mean, that's incredible. So again, where'd the mass come from? Ta-da, right? So here you have the mass of the electron and anti-electron, and they were going super, super fast, right? So some of this kinetic energy became the mass of the Z, okay? Just like Einstein predicted. They also use this accelerator. By the way, there's a highway that goes over this. So if you're ever near Stanford, you should drive out here and see it, you know. There's a highway, and you see this 2-mile long thing. You go, what in the world is that? Well, that's what it is, all right? Okay, so they also use this accelerator for this reaction. So they collide the electron and the positron, and you get light. Now, wait a second. How much mass does light have? 0, right? 0. So you started off with mass. Where'd it go? Well, where did it go? What did Einstein teach? Mass can be converted into energy. So all this mass, which is not a whole lot, granted, all of this mass was converted into energy because there's no mass here at all. And again, that just makes sense, right? Because mass can be converted into energy, right? And so this was the mass of the electron and the positron. Okay, this is 0 because the photons have no mass, right? Light has no mass. Okay? So there you go. Let's talk about our sun. So this is not visible light. This is X-ray. 4.35 billion, right, times 10 to the 9th is billion. 4.35 billion kilograms of matter are converted into energy every single second. So you see that, you go, my gosh, the sun's not going to last very long, right? Well, the sun's very, very massive. So it's going to live a long, long time. Don't worry about it. But this is incredible. You know, 4 billion kilograms of matter are converted into energy every single second in the sun. So that's, you know, that's just good old Einstein's energy equation, right? Okay, let's see. That's just that again, all right? Just there you go, all right? Mass being converted into energy. So, right, so this is 0. Okay? All right, nuclear fusion in the sun. So this is why stars shine. There's a process called nuclear fusion. So here, so you have 4 protons. They fuse together. Remember, protons repel, right? But when they're going so fast under a lot of pressure, they can fuse together. So they fuse together, and what's formed is a proton and a proton, a neutron and a neutron, and all this other stuff. Gamma ray, that's light. Neutrino, positron, neutrino, light. Okay, so here. Don't worry about the details. But so in, you know, or before, you have 4 protons. After the reaction, you have all this other junk, right? Now here's the fun thing. So you measure the mass of this, and you measure the total mass of that. And here's what's cool. The total mass of this is actually lower than this. So you, in other words, so you lost energy. I mean, you lost mass. So where did the missing mass go? Energy, right? Energy, right? Gamma rays, for example. So the mass decreased, and that missing mass was used for the energy. All right. Yeah, there we go again, right? Okay, so here's kind of this is an awesome book. And this is written for just any educated person. Anybody that takes this class could understand this book. At the Elegant Universe, they had a Nova series on this, written by Brian Greene. So here's a quote. Mass and energy are not distinct. They are the same basic stuff packaged in forms that make them appear different. Just as solid ice can melt into liquid water, Einstein showed that mass is a frozen form of energy, which can be converted into the more familiar energy of motion. So think about that for a while. Okay, now, so we're basically done, but I just want to talk about the scientific reaction to Einstein. Now remember, this was a one-man show pretty much. Einstein did most of this by himself. There was hardly any, there was no experimental evidence of this at the time. So most people just flat out didn't believe him. Okay, so let's see, relativity was published in 1905. Okay, that's when Einstein published it, 1905. So there was a meeting of the American Physical Society, that's all these physicists, right, in the United States in all right, so this one was published. And the APS meeting, so 1911, the American Physical Society had their national meeting. This is 6 years after it was published, for goodness sakes, right? Okay, so this guy, his name is William Maggie. He was from Princeton. He gave the presidential address. And he didn't think anything of Einstein's theory, so he's basically cutting it down, being real negative. All right, so he's talking about relativity. All right, here we go. This is a famous quote. So this relativity, this really amounts to saying that experience is not a criterion of truth, and that we must rely on an inward sentiment of knowledge as revealed in subjective formula. Now that's incredible. I mean, what is he saying? He's saying that you're supposed to rely on experience alone. Well, come on. Who here has traveled near the speed of light? Nobody. So does anybody have any experience traveling at the speed of light? No. Okay, and then he says, what? Look at this. You must rely on an inward sentiment of knowledge as revealed in subjective formulae. That's plural for formula. First of all, since when is a formula, since when is a math equation, since when is a law of physics subjective? It's not, it's objective, right? So anyway, so he's basically saying you should not believe formulas. You should believe your own experience, which we laugh at now. Okay, now here's another one. Same guy. Remember, Einstein, German, right? Undoubtedly, the German mind is prone to carry a theory to its logical conclusion, even if it leads into unfathomable depths. On the other hand, Anglo-Saxons, Americans, right, English, are apt to demand a practical result, even at the expense of logic. I mean, it's an incredible statement for a physicist. You're not going to believe logic? Incredible. But anyway, so like I say, we laugh at that. All right, let's, one other story about Einstein. So Einstein, he won the Nobel Prize much, much later. And he won the Nobel Prize for something called the photoelectric effect, which we'll learn about soon. And he was really ticked off because he felt that he should have received the Nobel Prize for relativity. Now, when you get awarded the Nobel Prize, you have to give a speech. And you're supposed to give the speech about what you received the Nobel Prize for, right? So everybody expected him to give the speech about the photoelectric effect, because that's what he got the Nobel Prize for. However, Einstein being Einstein, he got the Nobel Prize, and he gave the speech about, guess what? Relativity. So that's kind of fun. Okay, here we go. Let's just quickly review. So again, special relativity, it just means restricted. It's restricted to non-accelerated motion. The more general case is called general relativity, and we don't learn about that in this class. All right, so here's what we were supposed to do, the learning objectives. Understand and reason with the fundamental concepts of event and reference frame. You see how important that is. To understand how the principle of relativity leads to the relativity of simultaneity and length and time dilation and length contraction. We learned about the Lorentz transformations of position and velocity. Remember, Einstein had to change the Galilean equations. We explored relativistic energy and momentum, and we recognized the significance of Einstein's famous equation, E equals mc squared. Oh yeah, this is another awesome book. This is even better than the other one, I think. Einstein relatively simple. Einstein relatively simple brings together for the first time an exceptionally clear explanation of both special and general relativity. It's for people who always wanted to understand Einstein's ideas but never thought they could. Told with humor, enthusiasm, and rare clarity, this entertaining book reveals how a former high school dropout, Einstein, revolutionized our understanding of space and time. From E equals mc squared in everyday time travel to black holes and the Big Bang, Einstein relatively simple takes us all, regardless of our scientific backgrounds, on a mind-boggling journey through the depths of Einstein's universe. This is a really, really good book. Okay, let's review now. So this is what the important logical argument. The principle of relativity says that the laws of physics, electromagnetism, and mechanics are the same in all inertial reference frames. That is true. I mean, you prove that every time you go on a plane or on a train or anything. All right, so that's principle of relativity, which is true. Okay, a law of physics from electromagnetism says that the speed of light is constant. So if you take this, this is just logic. Therefore, the speed of light has to be constant in all inertial reference frames. Make sure you understand that. I mean, it's an easy logical argument, but when you think about it, it's completely nuts, right? Okay, time dilation, this is the equation. Proper time, dilated time. Here's this awesome graph. Here we are down here. We never notice it. But if we work with particles that travel near the speed of light, you do notice it, right? So like Velma, 1 second, but Mort says longer than 1 second. And so if Velma was going at 0.9 c, Velma says 1 second. What would Mort say? Mort would say, nah, it's like 2.2 seconds. All right? So time, there's your time and there's my time. If I'm traveling relative to you, we're going to measure the same event, like a sneeze or something like that. We're going to get different answers, and we're both right because time is relative. Okay, then there's length contraction, right? So again, that's the equation. And this time, we're down here again, so a meter stick is a meter stick, right? I mean, a meter is a meter, But if I'm going relative to you at like 0.9 c, then you're going to measure the meter stick to be like 0.4 something meters long. So, okay, so that's length contraction. Simultaneity, two events cannot be simultaneous in two different reference frames. This is what we learned in Physics 105. It works fine for slow things. Here's the correct equation. It works for everything. So you just have to add this denominator. So you're adding velocities. Nothing can go faster than the speed of light, and that works. Okay, relativistic momentum, right? Because the speed cannot exceed c, so the momentum goes like this. And again, the proof is Fermilab, where they have to crank up those magnets to keep those protons going in a circle. And then energy, total energy is conserved. This is the total energy. We worked out what that is. It's kinetic energy plus rest energy. Then we have this brand new equation for kinetic energy. And then this is energy conservation that shows that mass can be converted into energy. And then the Lorentz transformations, the yellow is what Lorentz or Einstein added. Time is not the same, distance is not the same, And that's it. Thank you very much. How's that for time, huh?